I have to say that, well, the theme of this lecture series is mathematics and computing. And so, well, I did my best to prepare a lecture that's within the theme of the lecture series, even though in some sense this is not my primary sort of area of research, if you want. And so I wanted to start this lecture by, asking ourselves an even more basic question, which is sort of what is mathematics, or what do mathematicians do? Now, of course, I recognize many faces in the audience, so this slide is not for you. I hope that there are a few people in the audience who are not professional mathematicians. And then, of course, in the sort of mind of maybe a more general public, so if you're not a professional mathematician, then you might think that mathematics is very closely related to computation. Like when you say something like just do the math, usually means do a calculation that gives you the answer somehow, right? And in a way, that's really not so much what mathematics is about. And the other point I wanted to make here is that sort of computing or computational computers, if you want, don't necessarily refer to computers as we know them in the sense of electronic machines. So this here is a room full of computers during World War II, right? And so a computer can also be just a person doing computations. And these are not research mathematicians, right? Like these are people who were trained for a couple weeks or something to do specific calculations. And they are not research mathematicians, right? So they are not, in a way, doing mathematics, so they're doing calculations. So instead, mathematics is really much more sort of exploration of this world of ideas, a little bit like this kind of Platonic idealized world where you have somehow these abstract ideas or abstract constructions that we make. And then what we try to do is that we try to study them by essentially pure logic, right? So we try to make statements about these concepts that we develop that are like true in some kind of absolute sense, right? So in some sense, mathematicians are really trying to discover somewhat absolute truth in a way. But of course, they're only useful in a way if they have some kind of links to reality, right? Like, of course, you can stay up in your cloud and come up with very abstract concepts and say things about it that are true, but then maybe nobody really cares about that, right? So you might want to say true things about things that are somewhat related to the real world. And there are kind of different ways in which mathematics links to the real world. So like physicists, so I guess there's a number of physicists in the audience, well, at least one. So at least theoretical physicists, in some sense, their job lies on this arrow in a way, right? So it's about sort of building the link between the actual real physical world and this mathematical world of ideas. But then also anybody, in some sense, more generally, right? Like anybody doing modeling, and so it doesn't have to be physics, so it can also be modeling in like financial markets, or it can be modeling of biological systems. I mean, by and large, mathematics is basically the language of science, right? And then, so what you do there is people take problems from the real world and translate it into mathematical problems that then can be analyzed with the tools of mathematics. And of course, today, well, since the theme of this lecture series is about mathematics and computing, and here computing really mostly refers to the actual, electronic computation machines. Computers play some sort of a distinguished role here in the physical world, in the sense that they're as close as it gets to a physical embodiment of mathematics. Is that if you, now, of course, it's not perfect either, in the sense that, for for example, we have a very precise mathematical model, if you want, of how a CPU or a computer is supposed to work. Or if you write a program, it's supposed to be completely deterministic, and you know exactly what is supposed to be the outcome of the program. Now, of course, it might happen that the physical computer is not completely perfect. There might be some cosmic ray that kind of hits the CPU at the wrong moment with a too energetic particle, and then actually some bit flips that wasn't supposed to flip. Right? But if we ignore this, then a computer is basically as close as it gets to a kind of physical embodiment of mathematics, in the sense that you can simulate or you can describe most of mathematics on a computer or in computing languages, if you want. And we'll see that also kind of goes both ways. Now, the other basic question here is sort of what's actually a computation, right? So what do we mean when we actually, so I kind of explained what mathematicians do, and I try to make the point that by and large, we don't actually just do computations. And so what is a computation? Well, in some sense, it's kind of difficult to give a very precise definition. So, different people might give you slightly different definitions. So here, the definition that I would give is that it's sort of a sequence of prescribed steps that's guaranteed to lead to some desired knowledge in a controllable number of steps. So if you're familiar with the notion of algorithm, it's sort of like essentially an algorithm, but that is somewhat guaranteed to terminate. Right? And so why is that? So there are two conditions here that are highlighted. Right? So there's sort of that it's guaranteed to lead you to something, and that it does so in a controllable number of steps, so that you kind of know in advance roughly how long it's going to take you to get there. And so why are these two things important? So, take as an example of, so this is an example of something that, at least intuitively, we can all agree that is something we cannot somehow solve by a computation, right? Which is like, is the Riemann hypothesis true? Okay, so the Riemann hypothesis is one of the most famous open problems in mathematics. I guess most mathematicians would believe that the answer to the question is yes, but nobody has a mathematical proof that actually shows you that the answer is yes, okay? And so here the desired knowledge is very easy. It's either yes or no. Right? And clearly, at least intuitively, it's not something that's amenable to just a computation, because otherwise somebody would have done it. Right? And so what fails here? Well, so there's one algorithm that you could do, right? Is toss a coin. If it's heads, you say yes. If it's tails, you say no. Half the time, you're going to get the right answer. But obviously, here it's not guaranteed that you get the right answer, right? You only get it half the time. And well, the example is sort of in jest, but it's actually somewhat serious, because you can come up also with probabilistic algorithms that do give you information, right? But those have the property, so those would sort of fall under the realm of calculations, if you want, but they have the property that you can improve arbitrarily the probability of getting the right answer, right? In the sense that you would want, for it to sort of count, if you want, as a calculation, you would want to have something where you say, well, if you do this random thing 100 times, then, well, maybe 99% of the time you're going to get the right answer or something. Whereas here, you cannot really improve on this, right? Like, okay, you can toss the coin half the time you get the right answer, but there is no way you can somehow improve on this by having a simple sort of randomized procedure. The other thing you could do is simply check all potential proofs. So as we're going to see a little bit later, you can formalize proofs. So in some sense, you can enumerate all possible proofs if you want. By and large, you could just say, well, write random stuff on a piece of paper. Look, all the possible things that you can possibly write, right? All possible books. There's many of them, but there's a finite number of books you can possibly write in a way. And then you just go through these potential proofs, and most of them are going to be rubbish. But then, maybe one of them at some point is going to either give you a theorem that the Riemann hypothesis is true, or is going to give you a theorem that is false, right? But of course, that one, we have no control over. Like, we don't know a priori how long such a proof would be, right? And so we don't have any kind of control on when this would stop, right? And so that doesn't count, if you want, as a calculation, because you have absolutely no control on how long it's going to take you to produce the answer. You know that eventually it's going to produce the answer. It would take much longer than the entropy death of the universe, probably. But eventually it would, but you have absolutely no control on the time that it would take it, right? So now that we have, if you want, somewhat agreed on what's a computation and somewhat agreed on what's mathematics, so how are computations kind of useful in mathematics? So traditionally, if you want, computations have been useful like since way before computers existed, right? And one way in which mathematicians use them is as, if you want, experimentation, to try to figure out what sort of things are true before trying to actually prove them. So you try to do calculations on special cases to get some idea of what's going on. And so here, this is some scan of a letter from Gauss to Encke from 1849. So that's almost 200 years ago. And what he was interested here is somehow the density of prime numbers, right? And so what is, of course, very well known. I guess Yuri even wrote actually a little note about this particular page here. So what's very well known is that the density of primes goes sort of like 1 over log n. So if you look at the number, if you look at primes around a million, well, the typical distance between successive prime number is about 1 over the natural logarithm of a million. And so what Gauss did here is that he actually computed like how many prime numbers are there below 500,000 and then below a million, below 1.5 million. And these numbers are actually surprisingly correct, right? Like they are not completely correct, but I think the biggest error is maybe like 9 or 10 or something like this. So they are amazingly correct, these numbers. And of course, they had to come up with all sorts of tricks to find them quickly, right? Because you cannot just go by hand through all numbers to a million and try to factorize them, right? So you have to come up with relatively quick ways to eliminate big chunks of numbers. Anyway, and so here they had, so he had the actual numbers that he counted, and then the numbers of the integral of dn over log n, which he computed. And then here was another formula, presumably by Encke, that he was comparing it to, which was somehow similar. And in the letter, he was saying that actually after the previous letter, he looked at the work of Lagrange, that Legendre, that Encke mentioned to him, where he actually has a formula that's even more precise. And so you see, so this is really a very important tool for mathematicians to try to get some intuition for, some question that you're interested in. So they were interested in the density of prime. A priori, you have no idea how dense they are. You somehow figure out that they get rarer and rarer, but you have no idea how the density decreases, right? And so you just compute them up to 3 million. You count them, and you see what's going on, and then you can make a guess, right? And so this is something that people do all the time. So here I just wanted to show you an example that sort of came up in my own research. So what I was interested in here is sort of scaling limits of interface growth models. So the sort of thing you can imagine is you have a two-dimensional region, and then there is a one-dimensional curve that separates these two regions. And this curve can fluctuate in some random way, and you're interested in how these fluctuations behave over very large scales. And so here is a very simple mathematical model for something. So here the curve is actually just it's this piecewise kind of affine function that always, at every step, it either goes up by a step or it goes down by a step. And then it moves over time, and the way it moves over time is you just pick up a point at random, for example, this one, and then if that one is a maximum, then you flip it to make it a minimum, right? And then you pick another one at random, maybe now it's a minimum, you flip it to make it a maximum. And if it's, well, maybe it's neither minimum nor maximum, then you just leave it as it is, right? And if you do that, then you can ask yourself, well, you get something like this, right? So that's exactly what you get if you do this. And now, okay, so here you can already see that, clearly, so here this is maybe, I don't know, 5,000 of these steps, and it runs relatively quickly. You can somehow imagine that this is already pretty close to some kind of continuum limit, in the sense that you probably don't really see that there's 5,000 steps in length. If it was 500,000, it would probably look more or less the same, actually, right? So this is what's called a scaling limit. So here is an example. So if you take, for example, a snapshot of this at a fixed time, right? So this is now, take the previous movie, freeze time, okay? So you just look at a snapshot, and now you kind of zoom out. And you see, as you zoom out, it basically always looks the same. Okay? So this is what's called the scaling limit somehow in mathematics, is if you have a mathematical object, which is typically somewhat random and fractal here in this kind of context, which has the property that you can kind of zoom out as much as you want, it always kind of looks the same. Okay? And then you're interested in these kind of limits that you get. So the idealized one, which is the one that looks exactly the same at every scale. And here, these two parabolas, they are here to indicate the way in which you scale things as you move out. So somehow, when you zoom out by a factor 10 horizontally, you have to actually zoom only by square root of 10 vertically in order to keep the picture always kind of the same. Okay, so that's descaling that would leave that parabola the same. And if you take the same movement, but this time, instead of randomly, like when you pick a maximum, make it a minimum, and when you pick a minimum, make it a maximum, you sometimes when it's a minimum, say, you don't do anything. Whereas if it's a maximum, you always flip, right? So then you've biased towards one of the two directions. And then you get a limit which, a priori, if you don't know what to look for, looks exactly the same. But it's actually not. So if I somehow show it, the thing is, if you look at snapshots, it's a theorem that you cannot distinguish them. So you really have to look at the motion. And the way you can distinguish the motions, if you want, is that this motion, if you sort of look at what happens on the screen, it moves more sort of up and down, right? Whereas the other motion, you sort of see it moving, it looks more wobbly, right? It's sort of, you have the impression that it moves a bit more like sideways also. Okay, so so there is a theorem which says that like these two processes are, and this one also looks like it moves faster, and that's actually also a theorem that it does actually move faster. And so these have really two different large-scale behavior, even though they look quite similar because when you take snapshots, they're the same. And so then the question was whether, if you take other kind of, so here that's these two large-scale limits, and they have names. So one of them is called the Edwards-Wilkinson model. The other one is called the KPZ fixed point. And then the question is, if you have other models of this type, whether they would have the same kind of limit or if they have different limits. Are there like lots of different limits that you can get, or are there only like two of them? And it seems like most of the models that you would come up with would converge to one of these two, actually. Most of the ones that have similar feature in the sense that, it's sort of random, it's somewhat local, like if you you do things in a somewhat localized way, it's somewhat independent and so on. So for example, one thing you can do is you can have just sort of bricks falling from the sky and then pile up, but also stick to neighbors, right? So then the conjecture here is that it's exactly the same limit as this KPZ fixed point, so as the second example previously. And so at the time, so this was somehow a few years ago, we asked ourselves, so here if you look at this evolution here, what does it mean to have a brick fall down and sort of stick to the neighbors or pile up? It means that you change, if you think of h of x as being the value of the highest brick above the location x, it means that you update the value by saying the new value of h should be either the value at x minus 1 or the value at x plus 1 or the current value plus 1, right? So either it sticks to the left or it sticks to the right or it goes up by 1. And what it should do is the one that gives you the highest value, right? Because it does the thing it encounters first as it falls down. So the new value is sort of the maximum between the value on the left, the value on the right, and the current value plus 1. Right? And this is somehow a kind of a well-known mathematical conjecture, if you want, or actually physical conjecture. It's physicists who came up with that conjecture, that this particular model should converge to this KPZ fixed point, and it's known to be a very hard mathematical problem. So like nobody knows how to prove this. And so what we did with a postdoc is we thought, well, we try to come up with a simpler version and try to show that this simpler version converges to this simpler limit, which is this Edwards-Wilkinson limit, and then try to do some kind of interpolation between the two. And so what we thought is the natural simpler version is the one where instead of looking at the maximum, you just pick one of the three values at random as your update step, right? And then that's somehow the simple version. And then we think, well, then we can kind of interpolate a bit by sort of biasing a little bit, by sort of making the higher value more likely than the lower values. And then that should be a little bit like what I showed you before, where you somehow say, well, I make these flips a bit more likely than these flips, for example. And so in this case, so here is a simulation of what you get for this. So this simulation here, it's actually not exactly the same. So here, instead of having bricks of size 1 falling down, I have Tetris bricks falling down. But it should be the same thing, right? So this is really just Tetris bricks falling down and then piling up. Right? And then you can kind of zoom out, and you see something which is very similar to what we had before, right? So that's like the second simulation. You see it does the more wobbly kind of movement, right? And so then we thought, okay, so now if we do this thing where we choose one of the three values at random, then maybe we get the thing which is closer to the first simulation. And we tried to prove that. And so first we tried for a couple months to prove that, and we didn't succeed. And then at some point we thought maybe it's actually just not true, right? And so in the end, I kind of sat down and I did the computer simulation and found that the thing that you get is this. And so clearly it's completely different, right? So you have these towers, right? So if I freeze this, it certainly looks very different from what I had before. You get these kind of big cliffs, right? And so you get a completely different kind of scaling limit here. And then, of course, once you see the simulations, and since the model is quite easy, once you've seen the simulation, you can sort of guess what the scaling limit is, and you can actually analyze it, and you can describe it mathematically, and so on. And so it's kind of a nice model to analyze. But the point here is that it was important for us to actually just at some point just say, well, instead of trying to prove this thing that I don't manage to prove, let's just sort of cheat and see what the answer is, right? And so we just do a simulation, look at it, and then you see either it's the thing that I want to prove or it's not, and here it's actually just not. And then you change your mind and you try to prove something else, right? Right. So what I wanted to touch on some different aspect of how computation somehow link in with mathematics, which is much more recent kind of developments, right? And so that somehow started in the 70s, the 80s, which are two different ways in which computers somehow affected mathematical proofs. And the first one is what we would call computer-assisted proofs. And that would be situations where you come up with a proof of a statement, and so it's a completely human proof of the statement, except that at some point it relies on the output of some computation, and the computation is just too long for you to be able to do it by hand. Right? And then you would ask a computer to do the calculation, and then if you want that part of the proof would be also showing that the computer program that does the computation does really do what it's supposed to do, right? And so ideally, if you want that to be also human readable, you would want to have a very small and well-written computer program that you can actually convince yourself that it does what it's supposed to do, right? And I guess one of the first examples of such a theorem is the proof of what's called the four-color theorem, right? So the four-color theorem, I guess most of you have heard of it. It's the one that tells you that if you take any kind of map, so really map in the sense of geography map of countries touching each other, except you imagine, so countries are not allowed to have like enclaves or something, so they have to be connected countries. And the theorem says that it's always possible to color the map with four colors in such a way that neighboring countries have different colors. Okay? And we can assume that you don't have more than like 3 countries touching at a point. If you have 4 of them touching at a point, you can always slightly expand it so that it's only 3. Right? And so that was a long-standing open problem. And Appel and Haken in 1977, so they proved it, but their proof was assisted by a computer. So in which sense? Well, in the sense that basically they reduced the proof to a collection of about 2,000 or something elementary cases of which they had to show by hand that you could color them, or that it was impossible not to. And so there was part of the computer program. So they used partly computer as an exploration tool in the same way as what I just explained now, to try to figure out what are the possible obstructions or what are the possible cases that are relevant. But then also they used it to actually verify the cases that they managed to reduce themselves to. Right? So that was one of the first examples where you ended up with a proof that in some sense would not have been possible to produce that proof about before the late 70s, right? Because before that there was basically no computer that was sufficiently powerful to be able to do the calculations that they did. And writing out the proof would just be too long for anyone to, well, either write it up in the first place and then actually verify that it's correct. So that's computer-assisted proofs, and that in some sense it's still relatively rare, right? Like so most proofs that mathematicians come up with are not computer-assisted, right? So it's still the case that most of the time we use computers as sort of an exploration tool, but occasionally you have maybe pieces of a proof that rely on just some very large calculation, and then that might become part of your proof. There's a different development which is in some sense more recent, which is that of computer verified proof. And so that's very different, if you want, from computer-assisted proofs, in the sense that what you do here is that you use the computer to check that the proof is correct, right? Which is very different from either using it to somehow come up with ideas of proof or using it to do a calculation. So here, what you do is that there are computer languages that are essentially programming languages, but they are programming languages that are designed to allow you to express mathematical statements and mathematical proofs. And then the compiler essentially checks. So if the compiler manages to compile the program, that means that the proof is correct. And if the proof is wrong, then the compiler would basically tell you that there's an error in your program, right? So it's like a computer program, except that compiling doesn't really produce a program that you can then run. It's just the fact that it compiles means that the proof was correct, and if it didn't compile, the proof was wrong. Okay? And here, interestingly, somehow one of the first high-profile example of a proof that was computer verified is the same. So it's also the proof of the four-color theorem, but which was, so now the formalized proof was written by Gontier in 2005. And this now looks like this. So now it sort of looks like a computer program. Yeah. Okay, so this is, if you want, the statement of the theorem. So here is the statement of the theorem. It says, well, I guess it's somewhat human readable. And then, of course, the proof here is only 2 lines, but that's because there are, of course, pages and pages of proof that this relies on, right? So this is a very different thing, right? So here what you do is you write your proof in a formal language, and then you ask the computer to check whether you've skipped a step or not, basically, whether you've included all of the steps. Now, this is still relatively rare because it's an enormous effort to do that, because it means that if you have to break everything down really to the basic axioms, right? And when mathematicians write up a proof, even though we are very confident that our proof is correct, we tend to skip steps. And very often, if there are somehow some part of a proof that is a completely standard argument, we would just say, this is a standard argument, right? We would not write every single detail. Whereas, of course, that doesn't fly when you're asking a computer to verify it, right? Because the computer doesn't know about standard argument. The computer just checks what's in front of the machine and just checks the step one by one without having to understand anything about the proof, right? So it's purely about a mechanical way of verifying the steps to see if they follow from the previous steps. And so many of these, so the few theorems that have been formalized, the few sort of high-profile theorems that have been formalized, certainly the saying used to be that it takes about 10 times more effort to write a formalized proof than to write it on a piece of paper or somehow write it in the format that we're used to writing it for a mathematical publication. I've heard that by now it's more like 5 times because there's somewhat progress, but I guess it depends very much also on the different areas of mathematics. So now, of course, there's kind of an elephant in the room. So I haven't talked at all about ChatGPT and friends, right? And of course, sometimes you might hear, well, there have been a couple of high-profile successes somewhat recently. So about, these kind of large language models essentially winning a gold medal at the IMO. Or also, I mean, I guess some of you, I suppose that Terry Tao has talked about some of the work that he did or that he was involved in. So there certainly have been some like notable successes. And sometimes you then hear that, well, basically in 2 months, 2 years, whatever, the job of all the professional mathematicians in the room here would be redundant, and you just ask the LLM for, to prove the theorem, it's going to come up with a proof. So I would say for the moment, these reports of my death are greatly exaggerated. We're certainly not there at this point. I would say that most of the examples that you hear about are either extremely structured in the sense that you have certain kind of problem and then it comes in many, many variations. And if you don't know these variations, they might be hard to solve, but you can actually train also to, you can train for the IMO. If you don't train for the IMO, you basically won't be able to solve any of the questions. If you train for the IMO, then you will probably do substantially better. And just because you got the gold medal at the IMO doesn't mean that you're a good research mathematician or a bad research mathematician, I think. So it's really somehow different skill sets. And somehow the new theorems that were discovered so far, it was mostly also in the directions of statements that are somewhat open-ended in the sense of try to find the optimal constant such that blah. And then there's a theorem that says the optimal constant is less than 4, and then you have another one that says it's actually less than 3.8, and then there's one that says it's less than 3.72. And of course, you can imagine that then you can have more and more complicated statements that prove better and better bounds, and they sort of get closer and closer to the true value. And this is something that, like these automated theorem provers are actually pretty good at now. So that works quite well. So one way in which these LLMs are certainly being used by mathematicians at the moment is they work for generating ideas. So you can actually, especially if it's an area that you're not familiar with. Right? Like if it's an area that you're familiar with, then it would not really come up with anything that you wouldn't have come up with either, right? And it wouldn't really come up with it faster. But if it's an area that you're not familiar with, then yes, then it's basically like talking to a colleague who works in that area. And if you don't have a colleague that you can bother, well, then you can bother ChatGPT or so. And maybe half of the time what it tells you is complete rubbish, but at least it's typically not so difficult to actually check whether it tells you rubbish or not. And the other thing is, for example, explaining unfamiliar concept, that works extremely well. Now, one worry that one might have is that if it gets basically to the level of a strong graduate student, or maybe even like to the level of a PhD student, then it sort of cuts away this kind of middle layer. And of course, you need to go through that little layer to that intermediate layer to become an expert. And then at some point, it might become difficult to actually produce experts in an area because people never really go through the grunt work of doing little calculations to build some intuition and figuring things out at a lower level because ChatGPT can do it just as well. For the moment, my impression is that this is not really happening in the sense that when I see, I don't know, my PhD students or master students, they don't really seem to be affected by such a mechanism yet. But I think it's certainly something that we need to kind of maybe think about or sort of be on the lookout for. Now, in terms of where these whole developments are kind of heading maybe in the next 5-10 years or something, so I see somehow at least two potential uses that would make them useful for mathematicians. First one is essentially bibliographic search on steroids. So right now what happens is you can ask these LLMs, can you give me a reference for this and that theorem that I know about, but I don't remember exactly where I can find this particular version of it. Right? It would give you an answer that's plausible and that most of the time is wrong. Okay, so it would actually tell you, oh, you can find it in theorem blah of this book, and the book exists, and the book is on that area, and it has theorem blah in it, but that theorem is actually not the one that you're looking for, or the one you're looking for is not in the chapter, or it just isn't in that book. But it would seem plausible because the book is written by someone who is an expert in the same area, and there's certainly a very similar theorem in the book. And so if we were able to, and this is certainly, I guess, within reach of the sort of current level, is that, if you make sure that these things actually go in check, that the statement you want really is in the book and so on, then I guess having some kind of bibliographic search on steroids is certainly something that's doable with the current technology, like within the next year or something, if somebody wants to actually spend the effort and the money to do it. But that's definitely doable. Now, the other one is, in some sense, the linking between these large language models and the formalization of proofs that I just talked about earlier, right? So, which is that this formalization of proofs, it is useful because it gives you a guarantee that the proof is correct. And the problem is that, at least in some areas of mathematics, proofs are getting longer and longer, and things are getting more and more specialized. And so when you have a proof of a theorem that's a 200-page article, then you cannot ask the referee to check line by line every single step in the proof in a 200-page article, right? Because it would just take too long and nobody is willing to do it. Whereas if this was formalized, then the computer checks step by step. Right? So then you have a guarantee. If it works, then you have a guarantee that the proof is correct. And the problem is, as I was mentioning earlier, right now, the effort for producing a formalized proof is vastly larger than the effort for producing a proof at the standard that we are kind of used to. Now, what you could imagine is, and that's probably in some sense not too far from what the current technology can do, and there are certainly several startups who are definitely working on this problem, is you can imagine a situation where the mathematician provides a proof that is written more or less at the same standard of rigor and of completeness as we are writing it now anyway, right? So you would write it in the same way in tech as a proof, like the way you would write it for publication in a journal. And then you could feed it to this computer program that then would try to produce a formalized proof from what you've written, right? And I guess that's something that, at least for the somehow simpler statements or things that don't rely on massive amount of background materials or things that are somewhat self-contained, I think that's certainly something that we're probably going to see in the next couple of years. And that's something that would be, I think, useful also to somehow save some areas of mathematics from themselves, in the sense that it's not, in some areas it's definitely not sustainable to have proofs getting longer and longer, and nobody is able to actually check them all the way, and then you can have errors building up, and then the sort of fields can collapse. So I think this is certainly something that we should actually, in a way, kind of look forward to, that this would then be a tool that's used in the same way as everybody uses LaTeX now. Okay, but I think I should probably have reached, this light has turned red, so that means that I'm in trouble anyway. So I think I stop here, and thank you very much for your attention.
Yeah, I guess we have some time.
So I got to meet Ed Witten, and he thinks in exponents. How do you think, how do you visualize? He said that he expects quantum computing to be able to begin testing string theory at 10,000 qubits. So how do you, and what's your dream for what computers could do for what you're doing?
Well, okay, so I have no idea about quantum computing, so I don't know when that would get to anywhere, if it ever goes to somewhere. I think my dream would really be a tool like this, one of these two tools. I'd like to have that, because I think that would be something that would be massively useful to research mathematicians, both in order to navigate a literature that's expanding extremely rapidly. And so right now people specialize a lot because it's only possible to have an overview of a very small fraction of the mathematical literature. Right? Like if it was possible to find somehow references in areas that you're not familiar with in a way that's reliable and quick, that would certainly first allow people to kind of maybe work in a somewhat broader way, and would certainly also make it much more efficient. And then this auto-formalization in order to kind of somewhat try to mitigate the current, in some sense, the refereeing system is somewhat breaking down, at least in some parts of mathematics. And that would be something that could actually save it, I guess.
And how do you think? How do you visualize? Do you visualize in numbers, in proofs?
How do I visualize what? I'm not sure what.
I withdraw the question.
Sure how to use the microphone thing. It seems like it's working. I wanted to know, in regards to the worry that you brought up there, I'm in medical training, which is a field built on the intuition gained from technical grunt work. If this does come to pass and you start to see people's skills kind of dulling, do you feel like the field of mathematics and mathematics education would shift towards more cultivated problem sets and deliberate cultivation of skills further along into your career?
Yeah, maybe. I mean, in some sense, you see, I haven't quite decided if that worry is the same as simply being worried about having pocket calculators, and say, right, like which was a worry that people had back in the 70s when pocket calculators came up, and say, oh, every kid has a pocket calculator, they're not able to compute anymore, and so they won't be able to. So, of course, it's true. Everybody else, and probably, some people can be good mathematicians without being able to multiply two big numbers in their head. So in some sense, I haven't quite made up my mind yet whether this is a real problem or not, and whether it is somehow just like the problem with the pocket calculator, that in some sense you simply discard certain skills because you can offload them to a computer or something, and then you focus on the things that you cannot offload, and that there would still remain sufficiently many things that you cannot offload, and that the things that you can offload just become more efficient. And yeah, so I'm not sure.
Yeah, you mentioned earlier in your talk for many months, and finally you computed it and saw it wasn't true. So is this now a part of your approach to things? Have you moved up the computing phase earlier in the process?
No, so, okay, so this is, yeah, that's a good question. It's certain problems are more amenable to this than others, right?
Yeah.
And so it's in some cases you can actually just run a simulation and check things, and then you sort of you have an idea of whether something is true or not. You can simply. This is just not true for all, right? There are sort of many mathematical statements or things that mathematicians want to prove are not really amenable to that kind of verification. So it's just, it works for part of what you're doing. So personally, I mean, it happened, for me personally, I mean, it has happened a few times, but not many times, let's say, right? So like it happened maybe 3 or 4 times. That there was something like this where I actually ended up using a computer simulation in order to check what's going on and in order to set up a conjecture that I could then prove. Now, here in these examples, the computer doesn't help you to actually prove things, right? The computer just helps you to figure out what's true and what's not true, and to basically to set up a conjecture of what you want to prove. And then you still need to prove it the old-fashioned way. But yeah, so I've done it somehow a few times, but it's not something that I do like every time, or like I guess mostly by and large, I'm actually more interested in statements that are not really amenable to verification like this. But
you talked briefly at the beginning about computations being controllable. I wasn't sure I fully understood what you meant by that, like what constitutes a controllable computation versus like an uncontrollable one, like enumerating arbitrary proofs. Can you talk about that a little more formally?
well, okay, so so I guess my other point was that there isn't a good definition, right? So that means I cannot talk about it very formally because, I mean, I guess you can come up with formal calculations, right? I mean, there's theory of computation, but then chances are maybe you're more expert than me, and I mean, I'm really not an expert in theory of computation, right? I'm not a theoretical computer scientist. You can come up with lots of notions. You can come up with a formal notion of computability, right? And you can ask yourself whether certain expressions or certain functions are actually computable or non-computable. And usually that definition of computability involves some notion of actually having a guarantee that the thing terminates, in a way that's somewhat controllable.
So to follow that line, how do you know, for example, how do you address like undecidability of some mathematical theorems, right? So you could do the computation as long as you can, but that it could turn out that.
Yeah, so there are mathematical statements that are undecidable. I think people have a reasonably good intuition about what kind of statements have a chance of being undecidable and which ones are definitely not, or sort of are extremely unlikely to be. So for example, the Riemann hypothesis is definitely not the kind of statement that you would expect to be undecidable. It's usually the statements that might be undecidable are statements that quantify over extremely large classes of things, right? So they are. Okay, so now this is sort of a personal, my sort of personal opinion is that the mathematical statements that have a chance of being undecidable or could be undecidable are usually the ones that don't really tell you anything about the world. That would be sort of the provocative way of kind of putting it, in the sense that you wouldn't be able to somehow, right? Because by the fact that they're undecidable, it basically means that you would never be able to come up with some sort of calculations or something that tell you at least somewhat approximately whether they're true or not, right?